every day. Now, what did I do? That's so wonderful.
That is one genre and not the
What?
That's a genre.
Kenzie, hand back to you.
That would, is box, yeah.
No.
Do you think that
Yeah.
I don't listen to contracting documents. I think it's depressing. It is very depressing. Most of it.
Have you ever been to a Border
overnight?
concert? No.
Would you like to hear the best country song ever?
Yeah.
Are you gonna sing it?
I searched the world over and thought I found true love. You made another and you was gone.
That is beautiful.
Sing that one.
He's on from the 70s. It was a country TV show in the 70s.
you know what the best song is?
No.
The song is great, very good, people are crazy.
No. I disagree with a bunch of that. Anyway, all right, Heather. Time to get started here. Abel, I've got something to hand back to you, and then we will get going here. My plan is at the least to finish chapter 16 with you today. And so the whole idea has been done.
What?
The whole idea has been to take what we learned in chapter 14 and 15, those two chapters, and talk about, well, what are some practical considerations? And what are some things to watch out for? What are some cautions? So, we've already talked about, for example, how we need a simple random sample, no problems like non-response and things like that. But, in reality, not having those problems is unrealistic. So one of the things we looked at on Wednesday is when do we act like the sample we have is still representative? You know, if we can't get to all the adults in the U.S., if that's who we're trying to measure something about, would there be times when if I took a simple random sample of 30 people from every student on campus, there are times when I can say, yes, you are representative, and then other things that we might look at where no, college students would not be representative. Number two, what's our second condition?
Normal distribution.
Normal distribution. So after a quick look at one thing, we're going to talk about this some more. Remember that normal distributions are supposed to be symmetric. If you have an outlier, it could skew it left or skew it right. So I'm going to take an example from an earlier chapter to show you what would happen if you have an outlier versus what would it look like if you left it out, both for a confidence interval and for a hypothesis test. Would we include the outlier versus if we leave it out? And the third one. Right. So you don't know the population mean. That's the whole point of the inference, is either to get a confidence interval that might capture mu, the population mean, or just a claim about it. All right. So if I remember correctly, on Wednesday, towards the end, we had been working on page 400, Applier Knowledge 16.8. And there was a question about, is the result significant? So, page 400, 16.8. testing a claim that the population mean is 515. Or would it be actually greater than 515 as our alternate hypothesis? What was going on there was you people that take the SAT mathematics, the population mean is 515, but then we were talking about a subpopulation. Those who take it again and get special preparation or something like that. Does the special preparation make a difference? Oops. Greater. Does it make a difference? Would it make the mean in that subpopulation greater than 515? Or is the subpopulation, even after that special preparation, still like the overall population? So, let's see here. We're going to need, we already did this the long way, but we're still going to need it for the shortcut I'm going to do. What were sigma and n? Problem. Someone's got the book, turn to that page. Can you tell me real quick? Or if you've got it in your notes, what were sigma and n?
Sigma was 116.
Okay.
And N was 50.
N was 50. Okay. So there are two different parts. In the first part, you're testing the claim of is it 515 or is it actually the other claim greater? When your sample of size 50 gave us an X bar of, can't quite read it there, 541. And in part B, have that mean go up by just one little point. Up to 542. If I remember right, we did at least one of these the long way, figuring out Z and looking it up in table C, and then making our decision. Am I right about that? That we did one of those the long way? Okay. By the way, is this a one-sided or two-sided test? It's one-sided because we don't have these or not equal to part here. We have the strictly greater than. We pick the direction. Okay. So if we redo, what was alpha? Did the book give us alpha, or did I tell them alpha to use? How much? 0.05. That's the same as 5%. Okay. One more thing that's going to help is drawing a diagram if you're going to use normal CDF. And this might possibly need to be aimed at this part if it's not showing up over here. So put your claimed mean of 515. And either way, 541 or 542, which side of 515 is that? Is it below it to the left or above it to the right? 541 or 542, how's it compared to 515? Above. Okay. And in fact, both of them are quite a bit above. 541 is 26 above, right? The other is only one higher than that, 27 above. All right, let's see what we would get by normal CDF. Do I need to double it? No, it's not a two-sided test. But this will tell me since X bar is above the we want to see if it's far enough to the right to get into that small right-hand tail of that 5%. This side, since it's a one-sided test, all of that 5% we're talking about will be over in this tab. So that will help me set up what my upper and lower bounds are. Let's see, second and distribution. Normal CDF. So since it has a left-hand endpoint, part A has 541. What's our upper limit on this? So 10 to the 99, okay. We've got our claimed mu of 515. Yeah, 515. And the sigma, remember, we're not doing this for the population distribution of individual scores. We're doing this for the sampling distribution of X bar. So we'd have 116 over square root of 50, just like when we do this long way. Remember, if you do use this and I tell you to copy down the whole command, what I'm talking about is what it looks like when you paste it back into the home screen. And I will change the mode here so that you can see that whole line. Okay, there it is. We're getting the probability, then capital P, for when x equals 500, x bar equals 541. We round that to 4 places, 0.0565. How does that compare to alpha? Greater than or less than or equal to that? Greater. Okay. So that's greater than 0.05. That means we are going to do what? Fail to reject H naught or reject it? Fail to reject H naught. Remember to tell me on your homework if you just wrote fail to reject, put fail to reject H naught and read that full sentence. When you're asked for an interpretation, it's kind of weird. When you're asked for your decision, you say either you're failing to reject H naught or you're rejecting H naught. If they ask you for an interpretation, it actually winds up being about the alternate hypothesis. Are failing to reject, like failing to convict, would be equivalent to saying we didn't have enough evidence to say guilty. What we don't have enough evidence for here, in part A, is from the sample there is not significant evidence that the special preparation increases the SAT mathematics scores. Actually, I should say this. Increases the population mean of the SAT mathematics scores. So that's always, we're talking about inferring about the population mean. I think we'd actually done that on the calculator by the end of Wednesday anyway, and then we did the next thing, then the interpretation about the different results we didn't get to talk about. In part B, what if you had the same size sample, but in this sample they are just, the mean is just one higher, 542 instead of 541 for X bar. That's why having a calculator instead of doing it the long way is kind of nice, because you can make that quick change. Even if you can't do the scroll back and copy and paste like this version of the PI does, still it wouldn't take that long to type it in versus doing it the other way. How does that compare to alpha of 0.05? Less than, okay? And Danielle gave us the last one. What do we do here? Since it's less than, or if it was even equal to, what would we do? What would our decision be? Check. Okay. Now I was asking at the end of Wednesday's class, let's see, 0.0499 around 2. So we would reject H naught because that is less than or equal to 5%. Now, see, you're thinking, particularly if this is your first year here, you're thinking that 1 point difference, yeah, that would actually make a difference. There's two kinds of difference here. There's statistical significance. I would change from part A to part B. In part B, I would say, we have found significant evidence that the special prep increase does increase the overall population mean of SAT mathematics scores. Because I just went from something a little bit above 0.05 to something a little bit below it. Simply because the average in the sample went up by 1 point. And I can see how some of you would say, well, yeah, when you get admitted into college, they're looking at scores, right? ACT scores or something else, GPAs from high school. But then don't they also get references and you come to campus and you meet with them, things like that? So maybe if you were 1 point below some certain cutoff point, there might still be some way, like maybe it was a cutoff point of you start with 099 here, or you start with 156. There's a cutoff score for determining which one you should go to. Should you go straight to 156 if it's in your major? Or should you take 099 first? Well, if you're 1 point below, maybe you could get a reference letter written from a high school mathematics teacher, or take another test. Say, look how I did on that. There, I beat the cutoff point on that. Please, let me take 156. I don't want to take 199, right? So there's more factors involved, and you can talk to people and perhaps do something like that. So my point is, while it's statistically significant, which is defined back on page 377, we've got something that is below alpha, so it's such a low probability. Statistically, we say, yes, you've got significant evidence against H naught. But practically, the fact that was X bar going up by 1 point and making the switch by that 1 point from failing to reject H naught to rejecting H naught, I don't think that 1 point is of a practical significance. Practical significance and statistical significance then are not the same thing. Is this still catching up things over here, Sharon?
Yeah.
Okay. All right. I want to switch to another topic that they caution us about. What if there are outliers? And here's the reason why I have you holding on to your homework. We're going to jump back to page 365. And we're going to look at two examples involving confidence intervals. 14.19 and 14.21. both of them, we are supposed to come up with a 99% confidence interval. So if you look at table C, for 99%, you should find that's the 2.576, correct? 99% confidence, D star 2.576. Yes? Okay. So we use the same Z star in both. What else do we need besides Z star when we use the formula for confidence intervals? What other things are we going to need to fill in? N, that's one of them. What else? Sigma's needed. What else? No. U is not known. X bar. So we're using X bar to infer about U by getting this confidence interval that should have a 99% chance of capturing whatever mu is. Okay, so this should sound familiar. You have a class of 463 students, and you ask about how many minutes do you study on a typical weeknight. So we've got n equals 463, and X bar is 118 minutes. Does it sound like some familiar information? Also, okay, first question on the homework. You're doing a hypothesis test. Here we want a confidence interval. So X bar was 118. Z star, we just found from the table, 2.576. What was sigma? It should be the same as what was in your homework. Check what's in the book real quick. 65, both in the book and on your homework. Okay. And then N? 463. Okay. Who's got a calculator handy? Raise your hand if you have a calculator handy. Just two people. Oh, there's another one. Okay. Anybody in these two rows? I'm going to have you put in the subtraction one. Remember, you can put it in all at once. But if you do it one at a time, get your square root, then divide, then multiply. The last would be the subtractorette. You don't want to subtract 118 minus 2 point something and then try to multiply. That's not the order of operations. So these two rows do the subtraction, these four rows do the addition. And then I'm going to put what I got, and I want to see if I'm getting the same thing you were getting. Don't round until the end. Sort of looks like you've already got it done on the upper one, for the addition, 125.8.
Yeah.
Anybody else back that up when rounded to the tenths, the upper bound? How about you, Lala? You have the same? Okay. All right, what are we getting from the lower end when rounded to the tenths? 10.2. That's what I got. All right. If you look back at your notes, there's a couple things I'm addressing here. If you look back at the notes from last Friday, or if you watched the video that's posted from last Friday, I was picking some of those numbers about what the average population, the population's average healing rate was. Picking some numbers kind of out of the air about you, and then testing it. But I was picking stuff that was in between. And if I did a two-sided test, there was some connection between the confidence interval and a two-sided test. As a matter of fact, a confidence interval in itself is two-sided because you have the minus side to get to the lower bound and the other side, the plus, to get to the upper bound. So it should make sense that there's a connection between confidence intervals and two-sided tests. What was the claimed mu in your homework? What is the claimed mu? Michael? 120 minutes, which was converted from 2 hours. So we could have it match how the X bar was being measured. Okay, well, the fact that 120 is it in between these two values?
Yes.
Yes. This one's lower than 120, and this one's higher. So the claimed mu was in the confidence interval. You've got a 99% chance then that if it is 120, that it's in there. Your hypothesis test, what was the alpha used on the homework for the first question? 101 or 1%. Complementary probability of the 99%. Okay, so if I did a two-sided test, I'll bet we would come up with something bigger than 1% so that we would fail to reject. And I'm going to check that with normal CDF here real quick. Because 120 is in there. So let's see here. Because it's a two-sided test, H naught being mu equals 120, and HA mu is not 120, I have to double what I get from the normal CDF. If I were to draw my picture, my X bar would be below the claimed mu. So instead of going X bar to the right to 10 to the 99, I would actually start from negative 10 to the 99 on the left up to the X bar of 118. All right, what was mu? Mu is claimed to be 120. And sigma. We have 65 minutes. What was the sample size? We have to divide by the square root of that. What's our sample size? Probably the same in 14.19 as it is on the homework. What's the sample size? 463. Okay? So what I'm saying is I'm betting because 120 is in that two-sided confidence interval, and now we're doing a two-sided test, I think this is going to give us something bigger than 1%. In fact, it's a lot bigger. So that you would fail to reject the claim. 118 is not so far below to reject H naught. Fail to reject it, you have not brought significant evidence that mu is different from 120 minutes. Yes, sir?
How do you want us to prove that we have significant evidence?
Well, it's based on the number. So if you fail to reject H naught, you do not have significant evidence in favor of HA. If you do reject H naught, you do have significant evidence in favor of HA.
Okay, so it's just imagine.
So it's just based on the number that we got for P, or our estimate if you're using table C. Okay? Now, by the way, what did you get on the homework? Either for your estimate, what was P in between, or if you use table A or normal CDF, how does it compare to this? So I don't think you were doing the exact same problem in number 1, were you? What was different about the problem? Should still be 1%. So what is different about the problem?
One is just greater than.
Yep, it's a one-sided test, like this example here. So how did the p-value compare? If you use the table A, or normal CDF, and got a more exact value, did anybody do that? Use normal CDF, the table A. Okay, then what two values did you have P in between when you use table C then? Or if there was a single value, then it was greater than, or a single value was less than. What was the one value from table C or the two values? Somebody should be able to look from towards the end of their homework and tell me real quick. Tiffany?
What was the first one, right?
Yeah.
It was less than 0.674.
0.674. Okay, that's the z-score.
Yeah.
Okay. And then the probability,
And then it was greater than 0.25.
greater than 0.25. So in fact, take half of what I have for normal CDF there. And you're getting something that's a little bit bigger than 0.25. That's what I was looking for. This is about double what you had on the homework. Either method that you used. Okay. Well, even there you would fail to reject. However, if you look back at your notes from Friday, or rewatch the class by looking at the video that's on Blackboard, you may need a special plugin for your web browser to do it. It should be a free thing to get. Some of my computers that I have available automatically run it. Others I'm like, okay, gotta add something on. I have to figure out what the add-on is. But anyway, look back at that. You're going to see where I had some of the same values both in a two-sided and a one-sided test with the same alpha. In one case, I rejected H0, and the other I failed to reject. It's probably the one-sided test where I rejected, whereas my p-value was too high in the two-sided test. So when I'm making a comparison of confidence intervals to hypothesis testing, some people want to latch onto that and say, why do I have to do it the other way then? I can do all my hypothesis testing by saying, is mu, the claim mu, in here or not? And in this case, it is. So failing to reject H0. But you can only do that comparison since confidence intervals in themselves are symmetrical. They are two-sided. You can only make that comparison with two-sided hypothesis tests. A little more example here. In 14.21, just go to the next column over. They say, well, actually there weren't 463 in the survey. There were 464. And the reason they left one out, let's see if I remember the number correctly. Some of you read through it and tell me if I'm remembering it right. Somebody in the 464 claimed, I study 60,000 minutes a night. How many hours is that? More than there are in a day? That's 1,000 hours. That's certainly more than a day. Okay? So if that person had been included, that person would be an outlier. And what did they say X bar was when they include that 60,000 from that one individual? I think it was 270 something, I can't remember for sure. How much? 200?
Excellent.
Yeah.
47.
247. Okay. If I replace the 118 here with a 247, keep the 2.576 the same because it's still a 99% confidence interval we need. sigma is still the same in the population. This was a thing with a sample, not the population. And then finally switch the 463 to 464. Check my calculation here as well. I'm going to write it down first. When I round the lower and the upper bound to the nearest tenth again, getting 239.2 to 254.8. So check at least one of those, so I can get one person saying yes, the lower bound is right, and one saying the upper bound is right. Which one do you agree with?
I got the 239.
Okay. If anybody else gets that, let me know, or somebody can confirm the upper bound as well.
I got the upper down.
You got that? Anybody else backing up at least one of those sides? All right. Well, what if our hypothesis, for one thing, what's the effect of that outlier? It would make us think that the range of values that mu could be between would be much higher. What would it do to the hypothesis test if we do a two-sided test? If we still use 120, I'm going to draw the picture this time. Where is 247 in relation to 120? To the right hand side. Okay. In fact, I think we're going to find it so far right that it's going to be into that extreme range. We want a two-sided test with an alpha of 0.01. So we're talking about 0.05 over here, and, sorry, 0.01, so 0.005, and 0.005 over here. So now that X bar is on the other side of the claimed mu, double this. And now we would start with X bar of 247. What's the upper bound now, if we're going to the right? 10 to the 99. Okay. Anything else that needs changing on here?
So,
Change that 463 to 464. Well, this is a rare event, but this one is so small that the calculator can't tell the difference to 10 places. Really, it's probably some slightly positive number, a little bit bigger than 0. But so darn small that the calculator couldn't tell the difference between it and 0. This is virtually impossible. Is 0 less than 1%? 0% less than 1%? Absolutely. So do we fail to reject H0 or reject H0? Reject it. When P is less than or equal to alpha, reject H0. That should come as no surprise then with a two-sided thing of a confidence interval, and mu is outside it. How do I know that mu is outside it? Because that claimed mu of 120 is even less than the lower bound. If it's lower than the lower bound or higher than the upper bound, the claimed mu would be outside that. So in a two-sided test, since we already see this, it should be no surprise. We are rejecting H0. This would be saying that we have brought significant evidence that students study some different amounts, the mean of the population. The study time is different from 120 minutes. That's the problem with the outlier then. The person claiming to study 60,000 minutes a night has changed our confidence intervals greatly. And the outlier makes us switch from, if we include that person, to reject H0, when instead if we go, obviously this person's joking, There aren't even 60,000 minutes in a whole day, let alone in a weeknight. So, if you omit the obvious joke and use what are probably more realistic values for the rest, we get a more reasonable conclusion about what the confidence interval should be. And then we wind up failing to reject H naught. Well, then that's saying, yeah, you probably do study 2 hours a night. The population on average. Rather than either saying, no, they're slackers and study much less, or to go on the other side and say, oh, they're really good students and they're studying 5 hours a night. You know what I'm saying? So we're saying we haven't found significant evidence for a difference. It's probably pretty close in the population. It's about 2 hours. We want to be able to tell that if we kept that joke, here's 60,000 minutes in there. Questions? All right. Let's see here. Guess maybe we'll have time for one more thing here. Look back at this formula. I asked the same kind of question when we were looking at confidence intervals only. Which of these values in this formula can researchers have any control over? Versus things that are not changeable in the population or in the sample. What can they change? Can change anything. Okay. Actually, there's one other thing that's not in the formula, but is part of the process. Back here, besides being able to change n, what else were we able to change in terms of what we were plugging into the CI formula? Certain choice you can make that would change what? Tiffany? So change the level you want, change that percent, that's going to change Z star, right? We can then also change alpha. But the fact is, this is not changes to make afterwards. Real quick example before I pick something out of the book. This says 20 ounces. Let's say consistently somebody goes and buys a number of these from Local Jug. And then they find out how many ounces can go in there. And they're getting stuff like 18.8, 19.1, 19.2, 19.0. It's always less than 20. Well, that's just anecdotal information so far. Now they need to go get a sample, which they're going to say, they might say, here's the margin of error I'll accept, but figure out n in advance. Don't say I got 100 and that didn't give me what I want, so I'm going to go get another 100 more in my sample, or another 1,000 more. You would have to start all over again. And you might even just find the same thing you found before, whether you like it or not. So what I'm trying to tell you is kind of the ethics of this inference stuff is if you set an alpha in advance, you stick with that alpha. If you set an n value in advance, go get that sample size. Don't try to do more stuff later after you already know your results, just because you're not happy with the results. Does that make some sense? Since we can change n here, I want you to see what the effect is if everything else was the same, including alpha. We're going to look at Apply Your Knowledge 16.9 on page 400, and let's see if we can make a prediction. As n gets bigger, square root of n also gets bigger. So what would happen to sigma over square root of n as n gets bigger? What would happen to that part right there? It gets smaller, okay? But then you've got x bar minus mu being divided by smaller and smaller numbers. What's that going to do? Switch it around again to increasing, yes. As z gets bigger, what did we say happens to p? It gets smaller. So this is part of what I'm saying. If you say, I'm going to do this research and I need 400 subjects to get the results you like, that come on. If you don't like them, that doesn't mean, well, I'll just increase n so that I'm going to get a bigger z and therefore a smaller p, so that maybe I can reject the null hypothesis. We're going to see that in action here on page 400. Detecting acid rain. Emissions of sulfur dioxide by industry set off chemical changes in the atmosphere that result in acid rain. The acidity of liquids is measured by pH on a scale of 0 to 14. Distilled water has a pH of 7.0. Distilled is very pure water. Lower pHs indicate acidity. But normal rain is actually already somewhat acidic. And I'm sure that was true before human beings were ever around. So that would be stuff that had nothing to do with industry. I think it says 5.0 is a normal acidity from rain. Am I right? A couple lines in there, 5.0. And if it's less than that, then it's just called that we have acid rain. So we're going to be doing a one-sided test. Where the null hypothesis is no, it's not acid rain. It's just got the normal acidity, pH of 5.0. Versus a alternate hypothesis that it's going to be less. Because the time we're going to have to do this the short way with normal CDF, which you can check it with calculating Z, and then against your Z star and your one-sided P rho. Has somebody spotted what sigma and N are in part A? Well, actually, yeah, I think it applies to everything. What's sigma?
0.5.
0.5. So now it's 0.05, but 0.5. Okay. And actually, they give us some different n's. N is 5, or 15, or 40. Let's just take the first two. 5 and the 15. Suppose that we had an X bar of 4.8. Both when we had a sample of 5 and an X bar still of 4.8 when the sample size was 15. How would that change the conclusions? Well, 4.8 is less than 5. And I have a one-sided test, so I don't need to multiply that by 2. Since I have the 4.8 less than the claimed mu of 5, I would start with negative 10 to the 99 and go to 4.8. Claim mean of 5. Theta is equal to 0.5 was sigma, but what else do we need? Provided that Theta gave us the right number there, what else do we need?
Divided by 10.
divided by square root of n. So square root of, well, in the first part, taking 5. Let's see, there we go. Does it tell us what alpha is in the question? No? Okay. Well, even if it doesn't, there are times when the authors do that, and I think it's kind of sloppy on their part. But this is even bigger than 10%. Most of the ones we've looked at were having alpha of 1%, or 5%, or 10%. So very quickly, it's going to take like a minute, minute and a half. Since that's even bigger than 10%, what would you do at the 10% level? Reject H naught, or fail to reject it? Fail to reject because that's bigger than 10%. That's 18 point something percent. That means we don't have enough evidence that the population is acidic rain. Or, if you went with a lower alpha of 5% or 1%, still, that's bigger than the 18.5 something percent is bigger. If I change the sample size, though, to 15, we should find as predicted that that's going to give us a lower p-value. That's what normal CDF is giving us. It's a probability, a p-value. And it is lower. If 10% was the alpha we were using, I would be rejecting H naught. Because 6 point something percent is less than 10%. The other two common ones, at 1% and 5%, I wouldn't have enough evidence. But at the 10% alpha level, this is low enough. I'll stop here. We're going to be starting chapter 17 and do what we can of it on Monday. Then review Wednesday and have a test next Friday. Yay! Yay!
And what chapters will be over?
So, 14, 15, 16. I'm sorry, not 17. That's the review chapter. Chapter 18. Whatever we do on Monday is like a test. And then we'll get into that. And we'll do
Think about that for again. Do it again. Come on. Have a great weekend.
And will you be posted that?
Oh, yes.
But when we get that, yes, this weekend.
The tutor that we go to, is it gonna be in on Friday? Yeah, Friday.
Okay.
So.
So you'll be wanting to ask
When we
questions.
want
Okay, like on Wednesday, Thursday?
Thank you.
All right. Well, I don't know what that means. But it's on tape. I could cut it out.